Lyme disease. Okay, we're ready to go. So today we have our second to last lecture. We're continuing on rheometry. So we're going to talk about the various corrections that have to be made to capillary flow. And then I'm going to move on to briefly talk about some of the other flows that we use. So let me just review what we did last time. We're talking about the capillary rheometer. And after an entire semester of talking very theoretically about the flows, we have to become very practical and try to actually produce those flows. So this schematic actually is an accurate schematic of the Instron capillary rheometer, which is down in the sub-basement. And this one is a little different from our Gutford capillary rheometer, which is upstairs in my lab, in that it has a tapered entry region. And also, I don't know if you can see this, but this capillary actually inserts upward into the barrel. So it's a slightly different design, but the overall picture is the same, which is that you have a reservoir of polymer and a piston that drives the polymer into the very narrow gap. This isn't to scale. This is typically about 10 millimeters, and this is about 1, so 10-to-1 ratio. Now, there are all kinds of interesting effects that take place here that are not assumed in the most general flow, in the most general analysis, including entrance effects, exit effects, possibility of slip, and then the one we talked about in detail, which is how to actually relate this flow, which is not regular parallel plate flow, to the regular parallel plate flow that's referenced in the calculation of viscosity. So what we did last time was we related the cylindrical coordinate system to the shear coordinate system. And then we needed to be able to express shear rate at the wall, and shear rate at the wall and shear stress at the wall. The calculation for shear stress was very easy, and it starts from the momentum balance and just knowledge about very minimal things, that the flow would be theta symmetric. So in this case, if you would ever see a extrudate coming out of a capillary that was sort of twisting, violently twisting, you might wonder about your calculations, because we're assuming that there is no twisting. There's no theta dependence to this flow. This is also, we also assume a very long tube, so things are not varying in the z direction, and a symmetric stress tensor. With that, we got that the shear stress is equal to delta PR over 2L. The shear rate at the wall was much harder to analyze, and I spent some time on this, starting with a Newtonian fluid and a power law fluid. These solutions assume a constitutive equation, but we wanted a solution that wouldn't assume a constitutive equation, and that's what we did in class here. We started with the flow rate as a function of the velocity field and followed the Weissenberg-Rubinowitz derivation to get an expression. So looking back over the calculus that we did, we first did an integration by parts, which turned the velocity into shear rate. Okay, that was a way of taking our flow rate versus velocity expression and making the shear rate appear. Once we made the shear rate appear here, we did a transformation of coordinates so that the r coordinates became stress coordinates through the expression delta PR over 2L for the stress. So we took flow rate versus velocity and turned it into an expression that would look like something related to shear rate and stress. The rest was sort of mathematical cleverness. We made the transformation of coordinates, did a little bit of algebra to make the left-hand side be written in terms of the wall shear rate. And then we took the derivative of both sides with respect to the wall, I keep saying shear rate, it's shear stress. We took the derivative with respect to wall shear stress, which after a little bit of working gave us our final result, which was that the shear rate at the wall, when we took that derivative, this shear rate at the wall appeared. And we got the shear rate at the wall in terms of this derivative of the apparent shear rate versus this shear stress. The final expression that we got is this. It says that the shear rate in the wall for a material of any constitutive behavior is related to the shear rate at the wall if it were Newtonian, the apparent shear rate, by this expression. So look what we have here. This ratio, d natural log gamma dot A, d natural log tau r, is equal to 1 for a Newtonian fluid. So 1 plus 3 is 4, 4 over 4 is 1, and you get that the shear rate is equal to the apparent shear rate. When it's not equal to 1, you get the correction for the non-parabolic velocity profile. So this correction is going to give us what is the value of this shear rate very close to the wall when we have a non-Newtonian fluid. Here it is written on the slide. Here's the apparent shear rate, 4q over pi r cubed, and the Rubinowitz correction, the Weissenberg-Rubinowitz correction. So that is one of the main corrections that we use in capillary flow, but there are actually two others, and I want to talk about them next. One is the analysis due to Mooney that takes into account any possible slip at the wall. And the second is the Bagley correction, which takes into account those entrance and exit effects. And I'm also going to, I added a few slides this afternoon so I can show you how those calculations look. Slip at the wall occurs seldom, but it does occur. And it typically would occur in a system that has maybe a lot of filler particles, a lot of powder mixed in, because that type of material ends up with a texture that the polymer behavior is sort of screened away from the wall, and you end up just sliding on the filler particles. So what happens when there's slip at the wall? In our analysis, we're calculating the shear stress at the wall and the shear rate at the wall. And when the flow is slipping at the wall, like I show here, where there's a finite velocity at the wall, then the slope here, which is related to the shear rate, is less steep than it would be if there were no slip. So there's going to be the same velocity, the same flow rate that's pushing the sample, but you'll end up with a lesser shear rate at the wall. We can relate these by considering the difference between the average velocity without slip and then subtracting the average velocity with slip. So remember, we have the flow rate Q is equal to 4Q, excuse me. The apparent shear rate, gamma dot A, is equal to 4Q over pi r cubed, 4Q over pi r cubed. And that would be what I'm writing here. The measured flow rate gives an apparent wall shear rate here. This I can write as the average velocity because I can relate flow rate to average velocity through the usual way. And so 4Q over pi r cubed becomes 4 V average over R. So here is the measured 4Q over pi r cubed, and then we subtract the amount of flow rate that is essentially lost to slip at the wall. So when we write it in terms of velocity, what we're essentially taking is the net velocity, V minus V slip, is equal to the actual velocity that really gives a apparent shear rate at the wall. So we solve this equation for the average velocity. That's all that's happened between here and here. And we get a relationship between what we'd like to calculate, which is the slip-corrected shear rate, apparent shear rate, and the experimental apparent shear rate. So if we take our experimental apparent shear rate and plot and take data for a variety of radii of tubes, when we plot this experimental apparent shear rate versus 1 over r, we should get a plot with a slope equal to 4 times the slip velocity plus an intercept of the apparent shear rate. So this is a correction for apparent shear rate. These are Ramamurthy's data. So you see he did a variety of experiments at different radii of tubes. And for many of the experiments, there was no slope, meaning there's no slip velocity for this linear low-density polyethylene. But when he went to higher and higher wall shear stresses, these are wall shear stresses, delta PR over 2L, he got some non-zero slopes. So his raw data was flow rate and pressure drop. From geometry, you can create the wall shear stress and the experimental apparent shear rate, and then you can make this plot. Once you have the slope, you can go back and slip correct all of your apparent shear rates. In our lab upstairs, we don't do this correction. We don't have the right capillaries, although we did just buy some this year, so maybe this fall we'll be running this test. The second test for entrance and exit effects is very widely applied, and we do this in the laboratory in the fall. And this is a test that, in aggregate, gives us the effect of whatever's going on at the entrance and whatever's going on at the exit. Okay, so the philosophy behind this correction is that if we had a truly long tube, very, very long, then there would be no end effects. And so as we went to smaller, shorter and shorter tubes, the pressure drop would just drop and drop, and eventually you'd get this 0, 0 point. Okay, so when there are no end effects, pressure drop versus L over R goes to 0. So going back up here to the expression for wall shear stress is delta PR over 2L. So if at a constant flow rate, we produce a bunch of different tests for different capillaries, different L over R's, we should always get the same wall shear stress. So this is a constant wall shear stress, but at a variety of L over R's, it should have an intercept of 0 and a slope of twice the wall shear stress. When we actually take data, and this is Bagley's original paper, you do get a constant slope for a constant apparent shear rate, but you don't get the 0 intercept, and that's the net pressure loss due to end effects. So in order to correct each of these curves, we need to subtract this intercept off so that they all collapse and drop down to 0. So I believe I gave you some, actually I'm not sure what I gave you. I may have given you some data like this to manipulate on homework. This is Bagley's data manipulated by me. Okay, so what I did is I took his data and digitized it and used Excel to fit lines to the data. And so the intercept is the entrance pressure loss. So these final terms here are all the entrance pressure losses, and I could use them to correct the whole pressure curve. In addition, the slopes are also obtained, and those slopes are twice the shear stress. So that way I can essentially average the shear stresses measured from each different set of data in a linear regressive fashion. So in fact, I use these data points here as my shear stresses. I don't average the shear stresses from each one. I use the linear regression result. So for instance, if we did this calculation in Excel, each of these curves is at a different apparent shear rate. So these are the apparent shear rates. They each have an intercept. So for instance, the 250 intercept is 163. Here it is. And the slope of the gamma dot A equals 250 is 32. There it is, the slope. I take half of that to get the shear stress, and then in this case, I convert it to pascals. So from a Bagley plot, we get a correction for the shear stress at the wall. Fairly straightforward, although taking all this data is quite intensive because these are each different capillaries. This is a capillary of length, say 20 millimeters and diameter 1 millimeter. Here's another capillary and a 10 to 1. And then in the case of Bagley, he did quite a number of different lengths. Usually, you would need to do at least 3 to do this meaningfully. You can do as many as you have available. Once you've corrected the data for any of these 2 errors, the slip and the entrance pressure loss, then it's time to do the Weissenberg-Rubinowitz correction. And this is fairly simple. The derivation was involved, but the application is simple. All we need is this slope, the derivative of the natural log of gamma dot A versus wall shear rate, wall shear stress. So we already have in our Excel file this 4q over pi r cubed. So if we have the correction, we're good. In the case of the data on the Bagley plot, we've got, if I go back to this, we've got gamma dot A, we've got the shear stress, so we can plot them. So this is apparent shear rate versus shear stress. Turns out to be a straight line. This doesn't have to be a straight line. It could be a curve. If it's a curve, then every point has a different correction. In this case, it's a straight line, so there's a single constant correction, 2.0677 in the case of this data. And it's a very true line. So to apply the Weissenberg-Rubinowitz correction, here's the old data. Here's natural log shear stress, so the natural log of that column, the natural log of gamma dot apparent. Take the slope. There it is. I wrote the same correction for every data point. And then gamma dot r is this number plus 3 divided by 4. Okay? So the Weissenberg-Rubinowitz correction is then applied to gamma dot A, and we get the true shear rate at the wall. Yes, the true shear rate at the wall. So once we have that correction, we can then take the true shear stress divided by the true shear rate to get the viscosity. So the final reported data are viscosity versus shear rate. So we needed this apparent shear rate and the raw data for delta P to get the shear stress, but then we corrected first for the entrance pressure losses and then for the non-parabolic velocity profile. So in the case of Bagley's data, which is from the literature, this is the final viscosity, wall shear stress divided by wall shear rate, and it's a power law function. So just to summarize, the raw data is pressure drop as a function of flow rate. The final data is viscosity as a function of shear rate. And the corrections are the Bagley correction for entrance pressure losses, the Mooney correction for slip, which was not performed in this case, the Weissenberg-Rubinowitz correction, and finally the plot. So there is this fair amount of analysis needed to do capillary flow data. The analysis actually is very straightforward. I would say probably the most tedious thing about capillary flow rheometry is actually dealing with the rheometer itself, because it's messy and time-consuming to fill and then empty that instrument. But the advantage of this instrument is that it gives very high shear rates. So you see the shear rates here in Bagley's data go from 50 to 200. You can get to even higher shear rates with a capillary rheometer. The low shear rate regime you need to approach with a different instrument. For instance, the parallel plate or the cone plate rheometer. The parallel plate flow is, these plates are typically about 1 inch in diameter. They can go up to about 40 millimeters in diameter. The gap between the two plates is typically 1 millimeter, 1.5 millimeters. And so they have the advantage of using a very, very small sample size. This flow is also a problem with respect to shear flow, because although it is one plate sliding over another, there is a strain inhomogeneity. So for instance, if you think about the ice skater problem, if you're turning a flow like this, the material elements near the center for one revolution travel a much shorter distance than the fluid elements closer to the outer rim. So it's like the ice skaters going around in a circle. The one on the outer edge is going the longest distance and really has to work the hardest. So there is a similar strain inhomogeneity problem that's just like in the capillary. So in the capillary tube, we had inhomogeneous flow because this velocity profile is the velocity profile in a tube. In the parallel plate flow, the inhomogeneity is in the theta direction. And we need to be able to take into account that is strain inhomogeneity. So strain rate inhomogeneity. Okay, so the strain rate is a function of R in this flow, just like the strain rate is a function of R in this flow, not constant. Now the details of this flow are worked out in the text. The shear rate is given by R omega over H. That's because if you look down on the parallel plate, this is moving along at some angular velocity omega. So at some position R, this arc length is R omega. So if I translate that into the shear flow, that's this distance. And this is the gap h. So this is moving along with a velocity equal r omega, and this is the gap between the plates, and so gamma dot is equal to r omega over h. The stress varies also with radius. And so we have a little bit of a problem. We have to do a similar analysis that we did on the capillary tube. And it turns out to be exactly analogous to the capillary result. And you can even see by looking at the final result for the stress, the similarities. So there's again this stress strain rate slope that's needed, plus 3 giving a correction term, and it corrects the torque that is present at the rim to be corrected for the variation in rate throughout the gap, throughout the radius. So viscosity, steady shear viscosity can be calculated in parallel plate as long as this correction is properly applied. Now, in practice, people avoid the parallel plate for this reason. Because steady shear rheometry is a little bit more tedious than you'd like it to be, and because there's another option. And the other option is cone and plate flow. So remember that in this flow, the problem was that for a given velocity at a given radius, we have this velocity is varying with r, and the gap is not varying with r. And so when we take the ratio to get the shear rate, we get something that in the end is a function of r. The solution to this is the cone and plate. So at a position r, so some radial position here, this is done in spherical coordinates. If I would look and swing this around, again I have, if I look down from the top, again I have a flow where this arc length is equal to this radius times this arc, this angular velocity omega. So once again, when we translate that into the shear flow coordinate system, this is this velocity here. In this case, this is V phi. Now, what's different about the cone and plate compared to the parallel plate is the gap. Okay? Back in the parallel plate, the gap is always the same gap, h, 1 millimeter, whatever you chose for the gap. But in the case of the cone and plate, this gap is varying with r as well. Okay? So because this gap is varying with r, you can do the geometry. It turns out that this gap is r theta naught, where theta naught is this angle. So when you get the shear rate, you get r omega over r theta naught, and you get a constant. So the magic of the cone and plate is that the shear rate is the same. It's a homogeneous flow. The shear rate does not vary with gap position. And so it's no analysis needed whatsoever to take a viscosity with a cone and plate. The shear stress is also constant throughout the gap because the shear rate is constant, and it's related to the torque that's required to turn the cone. So you end up with a very simple expression, 3 times the torque over 2 pi r cubed. So you make a single data point measurement of torque, and then you divide that by the shear rate, and you get the viscosity. So really, by preference, the cone and plate is the instrument of choice. So typically, when you see viscosity versus shear rate for a complete set of data, there'll be some data points, maybe including a little bit of shear thinning, and then some other data points at a very high shear rate. So typically, these data are capillary, and these data are cone and plate. There's one additional fairly common geometry, which is called couette flow or cup and bob flow. And maybe you've seen this on a Brookfield rheometer. This is where you have a cup for a very fluid type of fluid, something like water or an oil. And you would put the bob in the center and produce a flow in this gap here. So it's this gap where most of the stress is generated. These bobs have different shapes. This particular shape is designed to reduce the amount of drag on the bottom surface. Okay, on this one, they use the expression for the cone and plate to account for the stress on the bottom. In this one, you attempt to trap an air pocket in there and reduce the amount of stress or drag on the bottom, and so that you can just neglect it. This is also a homogeneous flow, so there's a very straightforward set of formulas given in the text for the viscosity as a function of shear rate in this flow. This one is done in preference for low viscosity fluids because you can generate more torque in this instrument than you can in the small cone and plate. In the book, there's a discussion of the pros and cons of these various geometries. This is too small for you to read, but please take a look. It's table 10.3, and it compares the parallel disc, cone and plate, capillary, and the couette cup and bob geometry. For instance, on stress range, the parallel disc is good for high viscosity, as is the cone and plate. The capillary is good for high viscosity, but the couette is good for low. Other things I've talked about were shear rates, or whether it's homogeneous, and whether you have to do sample data handling. But there's some other things on this table you might find interesting. One is a discussion of flow stability. So the parallel plates, at steady rates, there can be some edge effects. And those edge fractures are actually the reason why we end up not being able to go to the highest shear rates in the cone and plate or the cone and plate or the parallel plate. Once you get out to these high shear rates where it starts to shear thin, the edges become quite distorted, and in fact, sometimes the sample actually exits from between the plates. One of the negative factors of the capillary rheometer is the effect of pressure. There's no pressure problem with the cone and plate, parallel plate, or cup and bob, but in the capillary rheometer, if I dial back here to our Bagley plots, sometimes at these very high L over R's, okay, very long capillaries, we start to see a little bit of an upward curvature of these Bagley plots. And that's because we're getting to very, very high pressures. And at those pressures, the polymers themselves can be compressible. So we always look for a straight line on the Bagley plots as well to see whether or not there's a pressure problem. Now I have just one more topic, which is the elongational flows. And although we don't have a full complement today, I think I'd still like to go through and do the teaching evaluations today. And I'll finish up on elongational geometries on Wednesday. And in addition, on Wednesday, if you have any questions about the final, I'd be happy to answer those as well. So please bring any questions you have that you want me to clarify on Wednesday, and I'll do that as well. Okay, so Andy, are you going back to the department? Can you bring the teaching evaluations back to the main office after class? Okay.